Where's this? Okay. Okay. Was okay. Okay. Welcome back, everybody. So I think I cut some of you off. I mean, I'm aware. I'm assuming that the people that just came back, like, let me put it this way. I'm under the impression. I think, did anybody get to a final answer? That's my question. And there's no right or, I mean, no one got to a final answer. Is that correct? And there's no shame. I'm just making sure. Okay. Does that mean you did get to a final answer? You did. And you were just, oh,
We got an answer. It is unclear whether that is the correct answer, but we did come up with an answer.
oh, okay. No, that's great. First of all, and by the way, thank you for showing video YouTube, by the way. Wait, okay. First of all, I'm glad you got to an answer. And there's no, I'm glad you got to an answer. That's impressive. I know a lot of us got stuck. That's also fine. When you, and it, whether it's I may ask you to share something in a minute, but let me ask you this. When you say that you got a final answer, I don't want to put you on the spot, but was your final, when you say you're not sure if it's right or wrong, is that a generic, like, we're never sure, or do you have a particular reason that you're doubting it?
I, as well as my partner, anticipated it being greater than the frequency of the wave in regards to the source, just like the first example was, because the two objects are getting closer to each other. But our answer is in fact lower than 500, which was not what I expected. So
Okay.
that's why I feel like it's not correct.
That is very fair. Okay, so that's great. No, and on again to everybody, and I'm watching the clock. And even if this ends up being the only thing we're doing, this is very valuable to me, to everybody. Let me say, wherever you are in this whole process, if nothing else, we're gonna get the correct answer before the end of the day. Let me say to everybody, well, let me say to that is awesome. Like to have made a prediction and then get an answer that doesn't jive with the prediction, and then to be able to have critical reasoning skills and say, well, something is rotten in the state of Denmark. Like, either my answer is wrong or my prediction was wrong, but something is not jiving here. Like, that is physics thinking. I'm totally down with the whole thing. And to cut to the chase, to not leave to cut to the chase, your prediction. Well, I should have asked everybody, but the prediction is correct. I agree with Jake's and Eugen's prediction, and maybe everybody else's. I should have asked you. I agree that if the source is moving in toward the receiver, I do believe that we should get a number that is greater than 500 again, just like we did before. And I think that prediction is correct. And I believe that, yes, if you didn't get a number greater than 500, then something did go wrong somewhere, probably with a minus sign, is my guess. We're going to find out in a minute. It may be as simple as a minus sign. To everybody, the minus signs generally tend to be the issue in this kind of problem. We'll see in a minute, but they do make a big difference. I'm also going to say to everybody, almost every semester, a problem like exactly this appears on the final exam. Like, I know I still owe you your other exams back, so I maybe feel bad even mentioning exams, but we're doing all this because almost invariably there's a big problem. And when I say on the final exam, I mean just like we're doing right now, where you're asked to do one case and then and make predictions, and then asked to compare to the other case, and you're asked to come to sort of larger conclusion about the universe about the two cases. So if nothing else, I'm just saying, hopefully this is not a waste of any of your times. But yes, the important thing is to track the minus signs sort of carefully according to this red picture that I made at the bottom of saying that the wave always travels forward. Oh, sorry. The reason I'm mentioning your exams also, quick thing to say, and then I'm going to do it. I'm just going to do it because, and you hopefully it'll be easier for you to follow now that you've all tried it on your own. You'll see where you went wrong. But one other thing, I know also from experience, if you just go to the web and type in Doppler effect, there are equations on the web that summarize the whole Doppler effect in one package equation. I know that. I'm telling you right now that the question on the final exam is always designed to only work out if you follow this procedure and not just plug into that equation on the web. Another day, I'll explain why. but this is just a word to the wise or a warning to any of you who's still with me. Like, I know there's an equation that looks like a fast shortcut to all of this. It's for reasons I won't go into right now. It is a terrible equation, and it doesn't actually make things easier. If it did, I would encourage it, believe me. But it looks like it does, but it doesn't. So just trust me. So this procedure is what we're trying to learn. Anyway, that said, I'm now going to do the procedure to analyze this last case. I would like to engender more discussion, but I know the clock is ticking. So I'm going to do the procedure. You're going to, and yes, I think I'm going to get an answer that's going to be greater than 500 if I do it right. So here we go. Blank one, I'm going to solve, but I'm going to do it a little bit quick. I'm looking at the time. Yeah, okay, we got 15 minutes. Blank one, I'm going to solve for the wavelength of the wave according to the source. I'm going to say that the wavelength of the wave according to the source equals the speed of the wave according to the source over the frequency of the wave according to the source. And now stop. I'm going to go a little fast this time because we just did it. And also because I know now you've all thought about it. Stop. I'm going fast so that I can and I don't bore you. Stop me if I go too fast, like please, or when I get to something that you got wrong or whatever. But I'm saying, okay, so wavelength WS equals VWS over FWS. Then I say to myself, VWS was not given. Only VWM was given. So I right away just cut to the chase and go, okay, VWS must equal VWM plus VMS. All that is going to be over FWS. Okay? Then I say, what is VMS? Now, it's not zero in this case. VMS must equal the negative of VSM. VSM was the thing that was given. The source is moving through the medium toward the receiver, right? VSM, the magnitude of it was given as 40. And if I look at my picture, the VSM, the source, is moving through the medium at the same direction as the wave itself. So it seems to me VSM literally is positive 40 meters per second. VSM is. Therefore, now again, stop me if I'm going too fast, or stop me if you want me to go back on this page. But if VSM is positive 40, then it seems to me that VMS is the negative of that, the opposite of that. So it's negative of 40. I mean, it's negative 40, right? And you might even say, but why? How do you know that you need VMS? Because of the pattern, like because VWM plus VMS equals VWS. Velocity of the wave relative to the medium, velocity of the wave relative to the source is the velocity of the wave relative to the medium plus the medium relative to the source. In other words, what I'm saying is this. I'm saying the logic of what I'm saying right now. The logic of what I'm saying is we need the velocity of that sound wave according to the speaker. Now, everybody agrees that the sound wave goes at 340 relative to the air, but that speaker is running into the air while this is happening. Therefore, the air is coming toward the speaker, right? That's what that negative sign means. The speaker, the source, the thing making the sound, is running into the air while it's making the sound. So from its perspective, the air is coming toward it. So it's sending out the sound. The minute the sound comes out of the speaker, it's trucking through the air at 340, but the air is coming back in. So it's like, in effect, the air is slowing down the sound according to the speaker. So the sound is emanating from the speaker at only 300 meters per second. That's what I'm saying in English so far. I'm just wondering, by chance, I hate to put anyone on the spot, but like Jake and Eugene, was that part still? Were you in agreement with that, or is that where the mistake was? Just wondering.
That's where the mistake was for
Okay.
us.
All right, fair enough. But it makes sense now. Okay. And you are not alone. Like that's a classic. All right. So yeah, that's why. Okay. So the wavelength now is is 0.6. Is that right? Yeah. 0.600 meters. That's the wavelength. Now, everybody notice this. I'm watching the clock. We got 13 minutes. We're not done, of course, but in a way, we've just done the hardest part. Notice that wavelength is smaller than 0.680. It's smaller than the one we got in the other case. All the given numbers were the same. It's the same note, a 500 hertz sound that's coming out. But now the wavelength is smaller. And now and if you're following me, you might be like, wait, I thought the wavelength was the thing that's always supposed to be the same. The wavelength must be agreed upon between the source and the receiver, and it will be. I'm about to go to plank 2, where I say the receiver is going to receive that same 600, that same 0.600 meter sound, but the wavelength, so the source and the receiver will agree on this wavelength, but it is a different wavelength from what happened in the other case. What I'm saying here is now when the source is running toward the receiver, it's shrinking its own wavelength because it's spitting out these sound crests. It spits out one crest and then it runs toward it. So then when it spits out the next one, they're closer together. This is a compressed wavelength compared to the other case because the source is moving. Okay, but the receiver knows that. The receiver agrees. Plank 2, I'm saying plank 2, the wavelength according to the receiver must still be the wavelength according to the source. It's just not the wavelength that we expected from the other case, but both the receiver and the source agree on it. So I go to plank 3. I reverse my procedure. I'm now going to say, okay, I'm going to solve for the frequency of the wave according to the receiver must be the speed of the wave according to the receiver over the wavelength of the wave according to the receiver. The speed of the wave according to the receiver was not explicitly given, but it is VWM plus VMR, right? All that is over wavelength of wave. Oh, something in the chat. I'm sorry. Or did I miss it a long time ago? Wait. Oh, okay, cool. Okay, awesome. Check. Private chat person. One shot. Okay. Now I say, okay, what's VMR? Well, it wasn't explicitly given, but VMR must equal the negative of VRM, and VRM was explicitly given as 0. So here's where our 0 is now in plank 3. Like, in other words, the receiver is not moving through the air. The air is not moving past the receiver. So I put a 0 in there, and I say, I'm almost assuming someone's going to ask me to go back, and I will almost be scared if you don't, but I'm just writing this before I forget. FWR equals VWM plus VMR all over lambda WR, but VMR is 0. So FWR equals 340 meters per second plus 0 all over 0.600. Now, does anybody want me to go back? You're fine? You're okay going once? Okay. So then FWR here equals equals an answer that was sent to me as a revision. Well, anyway, I'm impressed. Okay, I'm looking at the time. Okay. So first of all, this is the answer to this case. 567 hertz, higher than 500 as predicted. First of all, honestly, I know I'm going a little fast, but can Arity tell me, does that make sense of how to do that case? Like whether you finished it or not in the breakout rooms, does what I'm saying now make sense? Thank you, Sylvie. Okay. And thank you, Jake and Eugene. But like, I guess I'm specifically, I mean, I wish I had directly addressed the question that Ashton, Abigail, Marina, and Sulady and Isabella had. I did not. But does this address, do you feel that this addresses whatever you came to the main room for, you guys? Are we good?
I understand it a lot better now.
Wait, you do, okay, and you're being polite. I mean, you're not being. I mean, okay, I'll believe. I
still have to go back and process this because I don't learn right away. But for the most part, I understand it.
That is a very honest and very fair thing to say. It actually makes me believe you. Yes, no, and to everybody, look. I mean, okay. I totally appreciate that honesty. Okay, and then thank you. And I see Ashton and Isabella. Thank you. And I've got a couple more minutes to say. I mean, we've got till 7:10, but let me tell you one of the reasons I do two cases like this, I present one case, then you work on the second, and then I straighten out. Like, I so agree. God, I could go down this rabbit hole. But really, I totally agree with Marina. I don't want anybody to be fooled into, and I don't want you to try to fool me. I am not sitting here thinking, well, now that I've done it twice, isn't it obviously clear? Are we all set? Couldn't we take an exam tomorrow? Like, no, I hate that about school. Like, that's not how it works. We all have to think about this on our own and practice on our own, totally including me. Like, this would make no sense to me, even the second time. It wouldn't until I practice it on my own. But secretly, to be one of the reasons I do it once and then I have you practice it once and then you hit whatever wall and then I do it again is to just reinforce to everybody, yes, this is worth practicing. As long as you see that there is a there, as long as you see that there's something here that could make sense once you practice it on your own, but you also see that you do actually need to practice it on your own, that it doesn't just fall into place immediately. That's actually my job here to show you that, because I do want you to practice this, because I do want you to see it for the final exam. It will be on there. And because it has huge implications about the universe, believe it or not. In the last 5 minutes, I'm going to start to tell you what those implications are. But yes, it's always like this in physics. I'm trying to make you see that it is very straightforward ultimately, but it isn't like that. It's a perceive, but it's not immediately. Right. I totally agree. Okay, wait. We've got 5. Preach it. Okay, fair enough. Thank you. Oh yeah. Oh, and I totally. Okay, thank you, Isabella. That makes sense. About with it. Thank you, Ashton. But okay. All right. Cool. Preach. Okay, now. I want you to note, with 4 minutes left, first of all, yes, note that this number is higher, than 500. And note qualitatively, this whole thing is driven by the relativity of velocities. This whole thing is driven by the idea that Earth moving toward the sun is the same phenomenon ultimately as sun moving toward the Earth, or however you want to say it, right? But notice this. So yes, qualitatively, if the receiver comes in toward the source, we get a Doppler shift that's greater than 500. And if the source moves in toward the receiver, okay, we get a Doppler shift we get a Doppler frequency that's greater than 500. But also note, this is a little bit interesting. Like, and I am watching the clock. I promise I want to leave as much as you. Just notice, hello. Notice for this answer, we got 567 hertz, right? But for the other case,
It's 559.
thank you. You just saved me time. Thank you. Bye. Now that, even though I have 3 minutes left, that in itself is bizarre. Like what was totally right where I was with Jake and other people is like, okay, I should expect that this case will qualitatively just be, and this goes back to Remy's original thing. Like either way, it's a case of things coming toward each other. Like whether you're running into the wave or the wave source is running into you, yes, we would expect you to hit the waves faster. And the whole thing is because of relativity. But if you accept, or if you get what I'm saying about relativity, if you're like me, you might well expect that numerically we should get the same result, whether we're running into the source or the source is running into us. Why are the two numbers different? That is noteworthy. The 2 minutes left. Answer number one is, notice that actually something different happened. In the case of the receiver moving, standard expected wavelengths came out and then we ran into them. In the case of the receiver moving, we were encountering standard wavelengths at a non-standard speed. But in this case, we were encountering non-standard wavelengths at a standard speed. That too, you'll have to turn over in your mind, since I know class is about to end. But I'm saying something physically happened, something physically different happened in the two cases. In one case, regular old wavelengths were sent out, but we ran into them and hit them faster than we otherwise would. And in the other case, by running, we shrunk the wavelengths, and then the wavelengths were encountered at a normal everyday speed. That's two different phenomena. Why is that? Why is receiver to source not the same thing as source to receiver? Here's the fast answer for the moment. We're going to tie it back to the universe next time. The fast answer for the moment is that the relativity that's operating here is not source to receiver or receiver to source. It is source to medium is the opposite of medium to source, versus receiver to medium is the opposite of medium to receiver. In other words, what I'm saying with 1 minute left, I'm saying that the reason that the receiver to the source relationship is not symmetric is that the receiver to the source relationship forgets about the crucial role being played by a third frame of reference here, which is the medium. The medium is making all of the difference in this phenomenon. It's what the source is doing relative to the medium, or the medium is doing relative to the source, versus what the receiver is doing to the medium, or the medium to the receiver. There's no relationship between source and receiver. The relationships are to the medium. The medium is a legitimate, crucial, vital frame of reference in this phenomenon, acting as though it's a third object. The Doppler effect brings to light the vital importance of a medium when it comes to waves. We'll go over that more, and we'll do electricity and all that next week, and I'll give you your exams, I pray. But that's obviously been a very long day. You've been very attentive. I hope this makes some sense. But yes, turn this over and practice it by yourself, blah, blah, blah. I hope you have a lovely, lovely week. Thank you for being so patient. It is exactly 7:10. But if you have questions, I'm here. I'm not going anywhere until you go, but you can
Thank
go.
you, Professor.
Okay, have a good night. Have a good night. Okay, have a good night.
Thank you.
Thank you.
Yeah.
Have a good night.
Oh, good night, Professor.
Have a good night, all. Have a good night. Have a good night. You too. Good job. Good job. I'm looking. Yes, have a wonderful night. Yes, thank you. Okay. Whoa. Hello. 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 Goodbye.